Hello, today we begin a new series on electromagnetic radiation which will cover what is light, Poynting vector, Fresnel equations, polarization, electromagnetic waves on a metal and waveguides. Today we begin with what is light. The starting point and basis of all these videos will be Maxwell's equations, and here they are. Those are the four Maxwell equations which we derived in the video on Maxwell equations, which you can find in the playlist on electricity and magnetism. And if you're uncertain about what these mean, you may want to look at that video first, because these really are the foundation of everything we will need in electromagnetic radiation. These four equations are what are called the integral form of Maxwell's equations, because each of the equations has an integral sign at the beginning. We can use two theorems to convert these into what are called the differential form. So let's look at the two theorems. They are the divergence theorem and Stokes theorem. And as you'll observe, in each case they take an integral form of a vector dot product dA or dl, which are the two forms of the Maxwell equations, and convert them into derivative types of vectors. So if we apply the divergence theorem and Stokes theorem to the integral form of Maxwell's equations, we get the differential form of Maxwell's equations, and there are the four that we shall be using during the course of these series on electromagnetic radiation. I first perhaps need to explain what this funny symbol is for those of you for whom it is not necessarily familiar. The actual symbol is called del, and it applies as follows. Del dot v, this term here, is known as the divergence of a vector v, and it's simply d by dx of the vector plus d by dy of the vector plus d by dz of the vector. Del cross v is a cross product with a vector, and that's much more complicated. Let's just go through it. It's dvz by dy minus dvy by dz in the x direction, plus dvx by dz minus dvz by dx in the y direction, plus dvy by dx minus dvx by dy in the z direction. Don't expect you to remember that. That's just what the cross product of the del term with the vector v becomes. And believe it or not, we shall be using this later on. For completeness, del f with no dot or cross is called the gradient, and this is of a scalar f. And that's simply df by dx in the x direction plus df by dy in the y direction, plus df by dz in the z direction. So it's basically the combination of the gradients of, in three-dimensional space, of the scalar. That might be, for example, a temperature field. So you're looking at the rate of change of temperature in each of the coordinate directions x, y and z. And then we have what's called the Laplacian. This is the del term upside down, a triangle. So the Laplacian of v is simply the second differential with respect to x and y and z. So it's d2v by dx squared plus d2v by dy squared plus d2v by dz squared, and that is often called del squared v. So the Laplacian of v is the second differential, which can be represented as a del squared. Well, that's all the kind of mathematics we're going to need, and Maxwell's equations in particular. Now we're going to consider a wave, and typically the way we represent a wave, this is a wave, this is the wave function psi, and this is either x or t, depending on whether you want to measure the distance the wave is travelling or how the wave varies in time. And we represent that wave, or we can represent that wave, by saying that psi is simply a sine wave, sine of kx minus omega t. Now I should say that you could say that sine equals the cosine of kx minus omega t, or as we showed in my video on waves, you can also represent the wave as e to the I kx minus omega t. They will all work. It's just that for simplicity I shall use the sine wave term for demonstration purposes in this video. You can find what all these terms mean in my video on the wave function, my separate video, but just to remind you, the position is that k is 2 pi over lambda, where lambda is the wavelength of the wave, which is the distance between two consecutive crests, and omega is equal to 2 pi times the frequency, where the frequency is the number of crests which pass a particular point in 1 second. We know that the velocity of a wave is the wavelength times the frequency, and from these equations here you can see that the wavelength is 2 pi over k and the frequency is omega over 2 pi. So that means that velocity is equal to the wavelength, 2 pi over k, times the frequency, which is omega over 2 pi. The 2 pi's cancel, and you get that the velocity of the wave is simply given by the relationship omega divided by k. Or if you like, the frequency term divided by what's called the wave number. Now let's take my original wave equation. I said I was going to use the sine wave term, and I want to differentiate it first with respect to x. If you differentiate with respect to x, you bring the k outside and you change the sign to a cosine term. So consequently, d2 psi by dx squared, sorry, d psi by dx, we're just doing one differential at the moment, so it's d psi by dx is equal to k times the cosine of kx minus omega t. Now we'll do the second differential, so let's differentiate again. We now get that d2 psi by dx squared is, well, we bring the k outside, we change the cosine to sine, but then we also have to put a minus sign in front of it, so it now becomes minus k squared times the sine of kx minus omega t. But the sine of kx minus omega t is psi, so that's simply minus k squared times the original wave function. Now let's take that wave function, and this time we'll differentiate it with respect to time. So d psi with respect to time is equal to, well, when you differentiate with respect to time, you now bring the minus omega term on the outside, so you're going to get minus omega, and then the sign changes to cosine. And now we're going to do that again. We're going to differentiate again with respect to time. So d2 psi with respect to dt squared is equal to, now we need to bring another minus outside, so that will become plus omega squared. But the cosine changes to minus sine, so you now do get a minus. It becomes minus omega squared sine kx minus omega t. And sine kx minus omega t is psi, so that becomes minus omega squared psi. So now we've got two formulae which involve psi. Psi obviously equals minus 1 over k squared d2 psi by dx squared, and psi also equals minus 1 over omega squared d2 psi by dt squared. So let's just write those two things down. We can say that psi equals, just a reminder from here, you take the k squared onto the other side, so it becomes minus 1 over k squared times d2 psi by dx squared. But psi also equals from here minus 1 over omega squared times d2 psi by dt squared. Well, obviously the two minus signs on either side of the equation cancel, so we can forget about those. And if we bring the omega squared side on this side, so in other words multiply both sides by omega squared, you get that d2 psi by dt squared is equal to omega squared over k squared times d2 psi by dx squared. But earlier we showed that the velocity of the wave is omega over k. And consequently, omega squared over k squared is simply v squared. So we get that d2 psi by dt squared equals v squared, the velocity of the wave, squared, times d2 psi by dx squared. And that is known as the wave equation. It relates the second derivative of the wave function with respect to time to the second derivative of the wave function with respect to distance. Okay, so now we're ready to start to use Maxwell's equations, and we're going to take the third equation. And what that essentially says is that if you march round any closed loop of length dl, then the E vector, as it were, dot product with the L, so it's effectively the electric field times the distance around a closed loop, is equal to minus the rate of change of magnetic flux as you go round the loop. And by using Stokes' theorem, we can replace the third Maxwell equation by this form. Del cross E equals minus dB by dt, where B, of course, is the magnetic field. So here it is, Maxwell's third equation in its differential form. Del cross E equals minus dB by dt. Del cross E is known as the curl of E. Del cross is known as the curl. So what I'm going to do is a bit of mathematical manipulation. I'm actually going to take the curl of both sides. So on the left-hand side, I'm going to take the curl of E, and that's going to be equal to the curl of minus dB by dt. This is just mathematical manipulation. And that is equal to the curl of E is equal to, that's the same as saying minus d by dt of the curl of B. That is the same as this. Now, Maxwell's equations tell us what the curl of B is. The curl of B is mu naught into J plus epsilon naught dE by dt. J is the current density, and if there are no currents flowing, then J is 0. So the curl of B will simply be mu naught epsilon naught dE by dt. So, the curl of B is equal to mu naught epsilon naught dE by dt. That is Maxwell's fourth equation. And so consequently the right-hand side of this equation, which is minus d by dt of the curl of B, minus d by dt of the curl of B, will be minus d by dt of this term here. So that's going to be minus mu naught epsilon naught times, and now this is the second differential, d2e by dt squared. So this is the right-hand side of this equation. What about the left-hand side? Well, the left-hand side is the curl of E. And now you just have to look up mathematical identities. If you look up vector calculus identities on Wikipedia, that will give you this, but it's just a mathematical identity. The curl of the curl is equal to what's called the gradient of the divergence of E minus del squared, which remember was the Laplacian, times E. As I've said, that is simply a mathematical equality. Now let's just look at this term here, the gradient of the divergence, that's a dot there, of E. Well, we pull in now Maxwell's first equation that the divergence of E is rho, charge density, divided by epsilon naught. If there is no charge around, then rho will be 0. Consequently, this term will be 0. And you're left that the curl of E is minus the Laplacian, or del squared, of E. So now we've got that the left-hand side of this equation is minus del squared E. And the right-hand side of the equation we just discovered was this here, minus mu naught epsilon naught d2E by dt squared. And the first thing you can do obviously is cancel the minus signs. And just to remind you what the Laplacian was, it's simply the second differential with respect to the three coordinate directions. So consequently, del squared E is simply d2E by dx squared plus d2E by dy squared plus d2E by dz squared equals mu naught epsilon naught d2E by dt squared. And that, you should recognise, is the formulation of the wave equation which we derived just a little while ago. We just derived it in one dimension, but you can see what you've got. You've got the second differential of E with respect to spatial dimensions is equal to a constant times the second differential of E with respect to the time dimensions. That's exactly what the wave equation was all about. But you'll also remember that the constant of proportionality was v squared. In this particular case, because we've got it in this order, it turns out that v squared is equal to 1 over mu naught epsilon naught, because when we derived it before, the constant of proportionality was on the space side. We've now got it on, as it were, the time side, so it will be 1 over, which means that v, the velocity of this wave, derived from Maxwell's equations, is 1 over the square root of mu 0 epsilon 0. Now let me just remind you what these two terms are. Mu 0 is known as the permeability of free space, and it has a value of 1.256 times 10 to the minus 6 henries per metre. Epsilon 0 is known as the permittivity of free space, and it has a value of 8.854 times 10 to the minus 12 farads per metre. And those two constants were known about and had been measured in Maxwell's time. So all he had to do was to plug these two values into this formula here, and that gave him that V is equal to 1 over the square root of the product of these two constants, and that came to 2.999 times 10 to the 8 metres per second, which you'll recognise is extremely close to 3 times 10 to the 8th metres per second, which is the speed of light. Now, in Maxwell's day, it was already known that light travels at 3 times 10 to the 8th metres per second. Without even knowing what light was, people had measured its speed. So Maxwell got to thinking, because bear in mind, the way we've got here, all we did is we started with Maxwell's third equation. That was the starting point. We've simply manipulated it. We've taken into account Maxwell's first equation en route. We got to a wave equation which gave us a velocity term. We calculated the velocity term and it came out to be the speed of light. That's what made Maxwell say, maybe this equation, which is essentially an electromagnetic equation, describes light. Therefore, light must be an electromagnetic wave. Let's explore this a little further. Let's take 3 dimensions, This is the x dimension, this is the y dimension, and this is the z dimension. And we're going to have a wave which oscillates in the x direction and travels in the z direction. So this wave is travelling in this direction along the z-axis, but it is oscillating in the x component. There is no movement at all in the y component. We know that if this is an electromagnetic wave, it will be travelling at a velocity which equals 1 over the square root of mu naught epsilon naught, and that we've just shown is equal to the speed of light c. And we've just shown that this is an electromagnetic wave because it derives from Maxwell's in particular the third equation on electricity and magnetism. So consequently, this is a wave which has an oscillating electric field. All these fields here are electric fields. And we can represent that by the idea that at any point, I'm going to call it EX because it's oscillating up and down in the X direction. That is going to be E0, where E0 is the maximum height of the wave, times the sine of K, and now it has to be Z because we're actually travelling in the Z direction, minus omega t. Now we already know, because we've shown, that d2Ex by dz squared is equal to mu naught epsilon naught d2Ex by dt squared. That is just the wave equation. We know that's the case, we derived that earlier. I only need to have one second derivative in the space direction because the wave is only travelling in the z direction, so there is no travelling in the x or the y direction, so there will be no components in those directions. And mu naught epsilon naught, of course, we know is the constant of proportionality between the two terms, which enables you to calculate the velocity. Now I'm going back to Maxwell's third equation. There it is. The curl of E is minus dB by dt. The curl of E is minus dB by dt is Maxwell's third equation. Now remember that there is only a variation in the z direction. There is no change in respect of x or y, so any variation of dE by dx or dE by dy is 0. So when we look at the curl of E, we're only interested in differentials with respect to z. So here is the curl, well in this case I did it for just a vector, but the curl of V for V read E, we want the differential with respect to z terms, and there are only two. There's that one and that one. We've got essentially minus dvy by dz in the x direction and dvx by dz in the y direction. What we're saying is that the curl of E, because there is no variation in the x or y direction, the curl of E will equal these two terms, minus dEy by dz in the x direction, plus dEx by dz in the y direction. Those are the only two terms in the curl that actually have a by dz term in them. Anything with dx or dy has no value because there's no variation in those directions. But look, we don't have an EY term, we've got an EX. The field is only oscillating in the X direction. It's not oscillating in the Y direction. So that goes as well. And that means that the curl of E is only left with one term. And it's a term which is in the Y direction. Consequently, we can say that the curl of E is equal to dEx in the y direction by dz, and that equals the curl of E is minus dB by dt. And if this term is in the y direction, then this term must be in the y direction. Now, this term here, dEx by dz in the y direction. Y hat simply means we're talking about the y direction, so it just reminds us what we're talking about. If we write that out, Ex we know is E naught times the sine of that term there, so this simply becomes d by dz of E naught sine kz minus omega t in the y direction. Just always keep reminding ourselves what we're talking about here. And if we take the differential with respect to z, you bring the k out on this side and the sine changes to cosine. So this becomes k E0 times the cosine of kz minus omega t in the y direction. And that of course equals, from here, that equals minus dB by dt in the y direction. So this term equals this term. Now if we integrate both sides with respect to time, integrate b with respect to time, or dB by dt with respect to time, you're obviously going to get minus b in the y direction. Let's always remember that is equal to the integral of this term with respect to time. Well, if you integrate with respect to time, you bring a minus 1 over omega outside and you change the cosine to sine. So that will give you equals minus, now we've already got the k, so it's now k over omega times E naught times now the sine of kz minus omega t in the y direction. And the first thing you can do is simply cancel the two minus signs. So now that you've got b, which I'll now put in bracket y just to show it's b in the y direction, is equal to k over omega. Well, that is simply 1 over the velocity, which is the speed of light, which is c, times E naught times the sine term. Well, that's just Ex. So what we've shown is that where you've got an oscillating electric field in the x direction, you've also got an associated oscillating magnetic field in the y direction, and the relationship between the two is 1 over c. In other words, the b term is 1 over c times the e term. C times smaller, if you like. The b term is c times smaller. So to fill it out, we've now got that b naught sine k z minus omega t equals 1 over c times E naught times sine kz minus omega t. You've got two waves that are completely in phase. They are at right angles to one another because E naught is travelling in the x direction, sorry, E is travelling in the x, or oscillating in the x direction, but travelling in the z direction. B is oscillating in the y direction, but travelling in the z direction. And if you look at it, what that clearly shows is that the magnitude of the E vector divided by the magnitude of the B vector, or if you like, the magnitude of the electric field divided by the magnitude of the magnetic field at all points is equal to C. Just to remind you that the electric field is oscillating in the x direction, the magnetic field is oscillating in the y direction, and the whole wave is travelling in the z direction. So we can now draw this wave as we did before. Here is the x, y and z directions. Here is the electric field that we drew before with oscillating E fields in the x direction, but travelling in the z direction with a speed c. And now what we know is that there is an associated B field. This is the E field. There's an associated B field which oscillates in the y direction and is in phase with the E field. So that's going to look something like this, where the B field is in the y direction. Now I haven't obviously drawn it to scale because what we just showed is that the E field is c times bigger. The speed of light times bigger than the B field. So it's an E field is dominant with a very, very small associated magnetic field. But what you notice is that the E field is, as it were, at right angles to the B field, perpendicular to it. Both are perpendicular to the direction of travel, and they are in phase. There's one more thing that you may want to notice about this, that when you draw these waves, you always draw it so that E cross B is the direction of travel. And what that means is that if you take the E vector and turn it in the direction of the B vector, think of the corkscrew rule now. If the E vector turns in the direction of the B vector, then that will cause the corkscrew to go inwards. So E cross B causes the corkscrew to go inwards. That's the direction of travel. So always draw the electromagnetic wave in that way. That will be critical to some of the things that we will be coming to later. Finally, for this video, how do you produce electromagnetic radiation? Well, let's think about radio waves, which are electromagnetic radiation. This is the way you produce them. You take an aerial, which is essentially just a piece of wire, and you apply to it an alternating voltage. Now, I don't mean by that the alternating voltage, alternating current that you get out of the mains. The frequency of the alternating voltage must equal the frequency of the radiation you want to produce. Here in the UK, we have BBC Radio 2, which broadcasts on 88 to 91 FM, which means that one of its wavelengths is 88 megahertz. That's essentially the same as FM. That's 88 million cycles per second. So you would have to have an alternating voltage of 88 million cycles per second. And if you consider just one electron in that wire, what will happen when you make this end positive and this end negative? The electron will be attracted to the positive end. But that voltage is changing 88 million times per second. So the electron is simply being accelerated up and down the wire 88 million times a second. And as it does so, as it accelerates up and down, it generates an electromagnetic wave with that frequency. But why? Let's just think about what's actually happening. Here is the wire, and here is the electron. And because it's an electron, it's a charged particle, it will have an electric field associated with it, and that electric field will of course radiate out in all directions. In fact, because the electron is negatively charged, the field lines will be pointing in. But let's not worry about direction, that's not relevant here. The fact is there will be an electric field associated with a point charge where the field lines radiate out in all directions. Now let's consider that the electron is accelerated, as it will be, up to this point here. Of course, it's going to be accelerated up and down 88 million times per second, but all I'm thinking about at this stage is the journey from here to here in a time t. T is going to be very, very, very small because it's going to be doing this, as I said, 88 million times a second. But we will agree, will we not, that in the time t that it takes for the electric charge to get up to here, there will be actually a sphere, but for these purposes I'll just draw a circle. There is a sphere of radius c times t, i.e. the speed of light times t, the time it took for the electron to move up, where the outside world does not know that the electron has moved. Because in order for the outside world, outside this sphere, to know, that information that the electron has moved would have to travel at faster than the speed of light. So in the time t, the time it takes for this electron to get from here to here, there is a part of the outside world which is beyond the radius ct, where nobody knows yet that the electron has moved. Consequently, the field line associated with that electron, that field line has not moved because it doesn't yet know that the electron has moved. But inside the sphere, there is knowledge that the electron has moved and that the field lines are now here. Consequently, you've got this field line here is the equivalent of this field line here. Consequently, at some point within this sphere, there has to be a joining up of the two. This is the field line that doesn't yet realise the electron has moved. This is the field line that does realise that it's moved. And somewhere there's got to be what they call a kink, a joining up. And obviously, as time goes by, that kink simply moves further and further out as the outside world increasingly becomes aware that the electron has moved. So you've got a kind of a moving kink to say the electron has moved and the field lines have now changed. But of course, the electron then comes back to its original position when it is accelerated in the other direction. And that is going to generate a kink, but this time in the opposite direction. So now you've got a flow of kinks going out in that direction. So essentially what you've got is a kink moving in this direction, and then a kink moving in that direction, and then a kink moving in that direction, and then a kink moving in that direction. Just a constant flow of kinks in the electric field. And that flow of kinks, of course, is what is responsible for generating the electromagnetic wave that travels at speed c. Don't expect you to remember that. That's just what the cross product of the del term with the vector v becomes. And believe it or not, we shall be using this later on. For completeness, del f with no dot or cross is called the gradient, and this is of a scalar f. And that's simply df by dx in the x direction plus df by dy in the y direction plus df by dz in the z direction. So it's basically the combination of the gradients of in three-dimensional space of the scalar. That might be, for example, a temperature field. So you're looking at the rate of change of temperature in each of the coordinates, known as the divergence of a vector v. And it's simply d by dx of the vector plus d by dy of the vector plus d by dz of the vector. Del cross v is a cross product with a vector, and that's much more complicated. Let's just go through it. It's dvz by dy minus dvy by dz in the x direction, plus dvx by dz minus dvz by dx in the y direction, plus dvy by dx minus dvx by dy in the z direction. Derivative types of vectors. So if we apply the divergence theorem and Stokes theorem to the integral form of Maxwell's equations, we get the differential form of Maxwell's equations, and there are the four that we shall be using during the course of these series on electromagnetic radiation. I first perhaps need to explain what this funny symbol is for those of you for whom it is not necessarily familiar. The actual symbol is called del, and it applies as follows. Del dot v, this term here, is of everything we will need in electromagnetic radiation. These four equations are what are called the integral form of Maxwell's equations, because each of the equations has an integral sign at the beginning. We can use two theorems to convert these into what are called the differential form. So let's look at the two theorems. They are the divergence theorem and Stokes theorem. And as you'll observe, in each case they take an integral form of a vector dot product dA or dL, which are the two forms of the Maxwell equations, and convert them into... Hello, today we begin a new series on electromagnetic radiation, which will cover what is light, Poynting vector, Fresnel equations, polarization, electromagnetic waves on a metal, and waveguides. Today we begin with what is light. The starting point and basis of all these videos will be Maxwell's equations, and here they are. Those are the four Maxwell equations which we derived in the video on Maxwell equations, which you can find in the playlist on electricity and magnetism. And if you're uncertain about what these mean, you may want to look at that video first, because these really are the foundation